Hello everybody. Today we are going to discuss some topics of the paper Statistical Physics, Research Methodology and Disaster Management for 5th semester BSc Physics students of Kerala University. Let us start with some ideas of error analysis. That is, what is an error analysis? Why it is important? And then about significant figures. Then how to determine the number of significant figures in a given number, etc. Error analysis may be defined as the difference between the measured value and the actual value. Error analysis is the study and evaluation of uncertainty in measurement. Experience has shown that no measurement, however carefully made, can be completely free from uncertainties. We know that the whole structure and application of science depend on measurements. So, the ability to evaluate the uncertainties and keep them to a minimum is very important. In science, error does not mean mistake or blunder. Error in a scientific measurement means the inevitable uncertainty that attends all measurements. So we cannot eliminate them by being very careful. What we can do is to ensure that errors are as small as possible and to have a reliable estimate of how large they are. Measuring everything is limited by the measuring device you use. Every measurement involves errors. Thus, the result of measurement should be reported in a way that how accurately something can be measured. Normally, the reported result of measurement is a number that includes all digits in the number that are known reliably plus the first digit that is uncertain. The reliable digits plus the first digit are known as significant digits or significant figures. So, significant figures are used to determine how precise a measurement is. Significant digits in a measurement include all the known digits plus the one estimated digit. Now, for an example, if you say that the period of oscillation of a simple pendulum is 1.62 seconds, then the digit 1 and 6 are reliable and certain, while the digit 2 is uncertain. Thus, the measured value has 3 significant figures. Now, for another example, look at the ruler shown here. Here, each line is 0.1 centimeter. So, you can read the arrow on it as 13.3 centimeter, which is reliable. However, using significant figures, you can estimate the next digit, that is the first digit, which is uncertain. So, that will give you 13.30 centimeter. Now let us try this one. Look at this ruler. What you can read before you estimate is 12.8 centimeter. Now try to estimate the next digit. Yes, it is 12.85 centimeter. To determine the number of significant figures in a number, we have to follow some rules. First one is, when reading a measured value, all non-zero digits should be counted as significant. So the number of significant figures in this first number, that is 26.38, is 4. The next number 7.94 has 3 significant figures. So all non-zero digits are always significant.
There is a set of rules for determining if a zero in a measurement is significant or not. First rule for that is, zeros in the middle of a number are like any other digit. They are always significant. Therefore, the number of significant figures in the number 504 is 3. 60002 has 5 significant figures. 9.077 has 4 significant figures. Thus, any zeros between two significant digits are always significant. Next rule is that all zeros at the end of a number and after the decimal point are significant. It is assumed that these zeros would not be shown unless they were significant. For example, consider this number 138.200. It has 6 significant figures. If the value were known to only 4 significant figures, we would write it as 138.2. So the number 32.0 has 3 significant figures. 19.000 has 5 significant figures. 105.0020 has 7 significant figures. The next rule is that zeros in between a decimal point and a non-zero digit are always not significant. For example, consider the number 0.000000233. It has only 3 significant figures. Next is about the trailing zeros, that is the zeros after non-zero numbers in a number without a decimal are generally not significant. For example, consider the number 100. It has only 1 significant figure. Now for 250, only 2 significant figures. 160000 has only 2 significant figures. So zeros to the right of last non-zero digit are not significant.
Next is about numbers represented by scientific notation. Scientific notation is a convenient way to write a very small or very large number. Here the numbers are written as a product of a number between 1 and 10 times the number 10 raised to a power. For example, consider the number 5326, which can be written as 5.326 into 10 into 10 into 10, which gives 5.326 into 10 raised to 3. Now consider the distance from the Earth to Sun as 150 million kilometers, which can be written in standard notation that would have anywhere between 2 to 9 significant figures. Scientific notation can indicate how many digits are significant. Writing 150 million kilometers as 1.5 into 10 raised to 8 indicates 2 significant figures, and writing it as 1.500 into 10 raised to 8 indicates 4 significant figures. Now let us do some practice questions to determine the number of significant figures in numbers. The first one is 45.8737. Here we know that all the non-zero digits are significant. So the answer is 6. The next one is 0.000345. Here in a decimal, the leading zeros are not significant. That is, all zeros before a non-zero digit are not significant. So the answer is 3. The next one is 0.00078600. Now we know that the trailing zeros in a number containing a decimal point are significant. That is, all zeros at the end of a number and after the decimal points are significant. So the answer is 5. Next is 48000 point. Here a decimal point is placed after the number. So the zeros count in the decimal form and the answer is 5. Next is 48000. Here zeros don't count without decimal. So the answer is 2. Next is a scientific notation. 3.982 into 10 raised to 6. Here all digits count. So the answer is 4. Next is 1.00040. Here zeros between digits count as well as trailing in decimal form. So the result is 6. Often when doing arithmetic on a calculator, the answer is displayed with more significant figures than are really justified. Then how do we decide how many digits to keep? There are some simple rules for that. The first one is, if the first digit you remove is 4 or less, drop it and all following digits. For example, consider the number 2.4271, which becomes 2.4 when rounded off to two significant figures because the first dropped digit is 4 or less. Here the first dropped digit is 2. The second rule is, if the first digit removed is 5 or greater, round up by adding 1 to the last digit kept. For example, if we consider 4.5832, which is 4.6 when rounded off to two significant figures. Since this first dropped digit, which is 8, which is 5 or greater, so we have to add 1 to this 5. So the answer is 4.6. Now write the following into a 3 significant figure number. The first question is 1.3587. Here the first dropped number is 8, which is greater than 5. So we have to add 1 to this 5. So the answer is 1.36, which has 3 significant figures. The next question is 0.0027421. Here the first dropped number is 2, which is less than 5. So the answer is 0.00274, which has 3 significant figures. The next number is 2367. Here the first dropped number is 7, which is greater than 5. So we have to add 1 to the 6 and drop a 0 here. So the answer is 2370. The next number is 138523. Here the first top number is 5. So we have to add 1 to this 8 and we have to write zeros for these three figures. So the answer is 139,000, which has three significant figures. The next is a scientific notation. 1.3683 into 10 raised to 6 is 10 raised to 8. Here the first dropped number is 8, which is greater than 5. So we have to add 1 to this 6. So the answer is 1.37 into 10 raised to 8, which has three significant figures. Now write the following into a four significant figure number. First number is 4965.03. Here we have to drop this 0 since it is less than 5. So the answer is 4965. The second number is 780582. Here 8 is dropped. Since it is greater than 5, this 5 becomes 6. Note that you must include the zeros for the remaining digits. Next question is 1999.5. Here we can drop this 5 and round up the remaining to 2000. Note that you need a 4 significant digit. So put a decimal point here. So the answer is 2000 point. Next is about significant figures in mathematical operations. The first rule is in carrying out a multiplication or division, the answer cannot have more significant figures than either the original numbers. For example, consider the multiplication of three numbers 34.6 into 12.1 into 1.2. Here, this is the number having least number of significant figures, which is equal to 2. So, we have to drop these numbers from the answer. And this is the number at the last digit retained. So, the answer is 5.0 into 10 raised to 2. Here, the number of significant figures in this number is 2, which is the least number of significant figures in this group of numbers. Now let us have some practice questions. The first one is 32.27 into 1.54. The answer is 49.6958. Here, this is the number having least significant figures, which is equal to 3. So we have to round it off this number into 3 significant figures. So the answer is 49.7. Next is 3.68 divided by 0.07925. Here this is the number having least number of significant figures, which is equal to 3. So the answer is 46.4. Here the number of significant figures is 4. Here it is 1, 2, 3, 4, 5, 6. So this is the number having least number of significant figures. So the answer is 0.05985, which has 4 significant figures. Next is 3.2650 into 10 raised to 6 into 4.858. Here we have 5 significant figures. Here we have 4 significant figures. So the result is 1.54586 into 10 raised to 7, which has 4 significant figures. Now, the next number is 6.022 into 10 raised to 23 into 1.661 into 10 raised to minus 24. Here, the number of significant figure is 4. Here it is 4. So, the answer is 1.000, which has 4 significant figures. Now, consider the second rule. In carrying out an addition or subtraction, the answer cannot have more digits after the decimal point than either of the original numbers. Now consider the addition of three numbers shown here. Here, this is the number having least precise number, that is only one digit after decimal. So the answer must have only one digit after decimal. So we can drop these two digits and rounded off this 8 into 9. The answer is 3760.9. We have some practice questions here. Here we have only two digits after decimal point. So the answer is 0.71. Here there is no decimal number after decimal point. So the answer is 82000. Here it is only one number after decimal point. So the answer is 0.1. Here there is no number after decimal point. So the answer is rounded to 0. Now this is an example for mixed order of operation. First we consider the multiplication. Here the total number of significant figure is 4. So multiplying these two digits, the answer is rounded to 4 digits, 77.89. Now consider addition. For addition, this is the number having least digits after decimal point. So the answer is 239.6. Thank you all.